When Neil deGrasse Tyson made his unexpected revelation about Neptune, it not only had a strong impact on the astronomical community, it also shook the foundations of what was until now considered a well-understood corner of our solar system. Tyson, known for his ability to explain complex astrophysical phenomena, spoke to a packed auditorium during a recent symposium broadcast live worldwide. The entire world watched in awe as he presented findings suggesting that Neptune, the icy giant that dwells at the edge of our planetary family, may not be what we always believed it to be. Before we begin, we invite you to like the video and subscribe for more updates. For decades, Neptune was listed as the 8th planet from the Sun, a cold, blue sphere of gas and ice orbiting far beyond the reach of the Sun's heat. It was discovered in 1846, not by direct observation, but thanks to mathematical calculations made from irregularities in Uranus's orbit. Since then, our knowledge of Neptune has been based mainly on sporadic telescopic data and a single visit by the Voyager 2 probe in 1989. That brief mission provided limited images and data, showing a frozen and dynamic world with supersonic winds, massive storms, and a deep blue color. However, much of Neptune remained a mystery. Tyson's revelation changed that. The core of his announcement revolved around a series of recent observations using a combination of data from the James Webb Space Telescope and interferometric arrays from Earth. These observations revealed anomalies in Neptune's internal composition and behavior that do not match our current models of gas and ice planets. According to Tyson, what astronomers detected completely challenges the conventional understanding of Neptune's internal structure and how it generates its magnetic field. Instruments detected strange patterns in the planet's gravitational field, in its electromagnetic emissions, and even in its heat output, suggesting a much more complex and volatile interior than anyone had anticipated. What Tyson described was a Neptune with internal layers not simply organized by density or temperature, but altered by dynamic internal movements that seem to defy standard thermodynamic expectations for a planet at that distance from the Sun. Instead of a uniformly differentiated interior with a rocky core, a layer of frozen water and ammonia, and an outer gaseous envelope, Neptune appears to have a mosaic of interactive zones, with intermittent regions of plasma-like materials and unexplained warm zones beneath the clouds. These warm regions should not exist according to traditional models. Solar energy is too weak at that distance to generate them, and there are no signs of tidal heating from nearby moons with sufficient mass. Something internal is generating more heat than expected. Even more puzzling was Tyson's revelation about Neptune's magnetic field. It was already known to be unusually tilted and offset from its center, but recent data show that the field is not only skewed, but also varies erratically over time. Its structure appears to be in constant flux, with sections shifting and reforming in cycles that had not been observed before. This led to the hypothesis that Neptune's internal dynamo, the mechanism that generates its magnetic field, may be nothing like that of other planets. Instead of a convective metallic core or a layer of conductive hydrogen, Neptune could have a layer of exotic ices, undergoing chemical transformations under immense pressures, which generate charge flows responsible for this changing magnetic field. Tyson even raised a possibility that caused quite a stir among the scientific community, that these anomalies could indicate that Neptune is partially hollow or contains stratified cavities or pockets that act as resonance chambers for electromagnetic and gravitational energy. Although this idea is still speculative, it is being increasingly discussed and could revolutionize planetary science. A planet with such an internal architecture would behave very differently from the solid or gradually compressed spheres we assume in most models. The implications are profound. If Neptune is so different from what we believed, that forces us to reevaluate the formation history of the entire solar system. Neptune, according to current theories, migrated from another region after its formation. Its gravitational interactions shaped the Kuiper belt, altered the orbits of other planets, and possibly contributed to the ejection of a fifth giant planet in the early solar system. If Neptune turns out to be a more Chaotic or exotic entity, the history of our solar system's evolution could be much more complex and dynamic than described in textbooks. Another disturbing aspect mentioned by Tyson was the detection of irregular radio emissions from Neptune's atmosphere. Although it was already known that the planet emits radio waves due to the interaction between its magnetic field and the solar wind, these new emissions appear to come from deeper layers and have frequencies that do not correspond to what has been observed previously. Some researchers are considering that these emissions could be due to internal processes never before recorded, possibly related to quantum behavior within the dense interior of the planet, or natural phenomena that we do not yet understand, resulting from extreme chemistry under gigantic pressures. Added to this is the possibility that Neptune is hiding layers of exotic materials that until now had only been seen in laboratory simulations. Tyson mentioned growing evidence that the planet could contain superionic ice, materials that behave as both solids and liquids, where water molecules lose their hydrogen atoms, creating a kind of electrified soup. This phase of matter could not only explain some of Neptune's heat generation and electromagnetic anomalies, but could also be a key component of its internal structure. Under extreme pressures, these ices could move in large conveyor belts beneath the surface, generating currents and turbulence much more complex than those seen on Earth or Jupiter. Tyson also spoke about the planet's extreme winds, which exceed 2,100 kilometers per hour, from a new perspective. Traditionally attributed to differences in heating and rotational dynamics, recent studies suggest that they could be driven by thermal pulses from within the planet. If Neptune is generating its own climate systems from deep thermal instabilities or even phase transitions between materials under pressure, it would be the first known example of a planet whose climate is driven primarily by its own internal dynamics. This revelation also has important implications for exoplanet research. Exoplanets similar in size to Neptune, known as mini-Neptunes or sub-Neptunes, are one of the most commonly detected types of planets outside our solar system. If Neptune is so different from what we thought, these thousands of worlds could be just as different. The classification and modeling of these planets may need to be completely revised. Tyson emphasized that our assumptions about their composition, habitability, and evolution could be wrong. Finally, Tyson mentioned an even more theoretical but intriguing possibility: that Neptune's anomalies could place it in an intermediate category between planets and brown dwarfs. Although Neptune is far from having the mass necessary for fusion, its unusual internal heat and dynamic energy systems could place it in a zone that requires a new categorization. This could mean a redefinition not only of Neptune, but also of how we understand and label planets in general. It suggests that there is a much greater diversity of planetary types than we previously considered, not just in size or atmosphere, but in internal architecture. Tyson described Neptune as a chaotic system in equilibrium, a body containing constantly changing self-balancing forces, driven not by the slow decay of energy, but by its eruption from unknown processes deep within. This revelation also highlights the fundamental role of the most advanced observational tools. Without the James Webb Space Telescope and recent improvements in ground-based arrays, these patterns and signals would have remained hidden beneath the planet's dense cloud cover. Tyson was clear on this point. Our ability to truly understand the universe depends on the instruments we build to observe it. As we refine our view of the cosmos, the possibility of discovering more worlds like Neptune increases, complex, misunderstood, and ready to rewrite everything we think we know. The repercussions of this revelation will surely spark debates about the limits of our current scientific models. If one of our own planets can surprise us so radically, what else awaits us beyond? Neptune, once considered the cold and silent cousin of the inner gas giants, is now in the spotlight as possibly the most exotic member of our solar system. And with that, we are reminded of how little we really understand about the universe we inhabit. Tyson's announcement is not just about Neptune. It's about our relentless pursuit of knowledge, the humility of science, and the exciting unpredictability of discovery. If you liked this video, don't forget to like and subscribe to our channel for more updates.